All right, we have example 6 now, which is to calculate the surface integral over the surface S, which is the portion of this graph, z equals x plus y squared, and then they give us this domain for x and y. So, whenever we are given a function of x and y, so our graph z equals f of xy equals x plus y squared, we can use a particularly nice and easy parameterization. So in general, given z is a function of x and y for, let's say, x and y in some domain D, we can use the following parameterization. We can let x be u and y be v, or vice versa, it doesn't matter, just pick one. And then we can let our z component be what we get when we replace x and y with whatever we set them to be over here. So in this case, u and v respectively. So because I'm doing this generally, this is true for any function. I can change this function to anything we want and get the same result. It would still be this sort of parameterization in this format. So how about we just keep it written like this and go through all the motions of the problem. So for instance, in this case, to calculate, to answer this problem, we would need to find our partial derivatives next. Then we'd have to take the cross product of them. All right. Our cross product here would be I hat plus fu k hat crossed with j hat plus f sub v k hat. This would be I cross j hat plus f v I hat cross k hat plus fu k hat cross j hat plus fu fv k hat cross k hat. And of course, a vector crossed with itself is the zero vector. Then we have k cross j is negative I hat. I cross k is negative j hat, and I cross j is k hat. So then this will end up being the vector negative f sub u, negative f sub v, 1. So that is the cross product every single time. No matter what we change our function to. We change this function here, we get the negative u partial, negative v partial, and then 1. So then the magnitude of this, ru cross rv, is the square root of f sub u squared plus f sub v squared plus 1. Okay. Now one thing we'll notice here that I want to point out is that because we're really just letting x be a new variable and y be a new variable, it's still just a single variable to the first power. This is u to the first, this is v to the first. So this isn't, performing this substitution into this function, it won't change the format or the structure of the equation, right? Which is different than something like this. If our function, like let's say we have a function f of xy equals x squared plus y squared. If we let x equal, let's say, v cosine u and y equals v sine u, then we get f of u comma v equals v squared. So structurally, this changes a lot if we do this kind of substitution. Whereas if we do the substitution x equals u, y equals v, then this really only changes it to the symbols themselves change, but the actual algebraic structure of the function is the same. So whenever you do a substitution where the actual algebraic structure doesn't change, people are inclined to not even do the substitution. So oftentimes you'll see people leave things in terms of x and y. So underneath of here, I'll just note that if you choose to parameterize this as leaving your parameters alone, which I'm not in the habit of doing, but it's perfectly reasonable to do so, then you would end up having something like this. Your x partial squared plus your y partial squared plus 1 under the square root for your, excuse me, for your magnitude. So that's just something that if you don't go to u and v, that's the way it would look. Okay. So, yeah. So what I'll do here is let's go ahead and try it out in this. Let's just keep it the same here. Let's not do this, but I just wanted to at least mention that. So in this case, the double integral over the surface S z minus x ds would look like the following. This would be, well, what would our domain be? Well, let's actually go up here for a second. And if we look at our bounds here, if x is u and y is v, then we have u between 0 and v, and we have v between 0 and 1. So I can say v between 0 and 1, and u between 0 and v. In which case, this would be 0 to 1, integral 0 to v. Z would be u plus v squared minus u times the magnitude of the derivative, which would be the square root of our x partial squared, excuse me, our u partial squared, which would be 1, plus our v partial, which would be 2v, plus, oh, sorry, squared, this should be squared, 2v squared, oops, plus 1 let's see here, du dv. All right, so simplifying things, we'll have v squared, and then this will turn into the square root of 2 plus 4v squared. Du dv. Doing the first integral, the u integral, we'll get u between 0 and v, which will just be v. So this will become the integral from 0 to 1 v cubed square root 2 plus 4v squared dv. We can let w equal 2 plus 4v squared. So then dw is 8v dv. So 1/8 dw is v dv. We can then solve this equation here for, let's say, v squared. So v squared is w minus 2 over 4. And we can also change our bounds. W of 0 is 2, and w of 1 is 6. So this would become the integral. Let's see, we'll have 1/8 integral 2 to 6. We'll take one of these v cubes. So we'll split v cubed up into v squared times v. This v will be paired with this dv, leaving behind leaving behind a v squared term. So the v squared will get turned into a w minus 2 over 4. The square root will just become the square root of w, and then our v dv gives us the 1/8 and a dw. We should be able to factor out the 1/4 to get a 1/32. And then this really is just a to the 1/2. So then that can factor through, or distribute through, I should say, which would give us w to the 3/2 minus 2w to the 1/2 dw, which is not a pretty integral, but it is a Calc 1 integral. And so its solution is 1/30 times the quantity 6 root 6 plus root 2, if you fully polish it. All right.